Alright, we've returned from earlier today, and if I recall earlier today I was doing the squarified problem. Got pretty close, but there were a few optimization things that I weren't completely sure of. So that's what we're going to try and fix here. So if we bring up our previous code D, maybe just a quick rundown of the problem first. So our problem here is we have an array A and B is considered squarified if you can take any subsequence in B of even length and you multiply it, you get a perfect square. The product of the elements in any odd length will not be a perfect square. And we have to find the length of the longest subsequence of A that is squarified. What we figured out first is that in the squarified sequence you can't have any square values, since otherwise you get you can just take that single square value and that's length 1, but it's a perfect square since the product will just be itself. Once we've done that, then I think what I figured out is pretty much the way you can create a sequence of perfect square. A squarified sequence is what you want to do is since basically when you choose any one of these elements it's not a square, then after that you choose 2 elements, it is a square, 3 is not a square, 4 is a square, so on. Is we pretty much define 2 values, a base and the square multiplied by the base sort of thing. So in this case, one of the examples was 312, 312. We notice that every single value here is divisible by 3, which is not a square. But then the 12s as well, if you divide it by 3, then you get 4, which are squares. So you could have done even something like 3, 12, let's see, 75, that's 5 squared times 3, 27. Something like this also works. And it works because if you take any one of these values, you have 3 times some sort of square, which doesn't work. But then if you take an even number, you get 3 times 3, like an even number of times, and a bunch of squares multiplied together, and that will always make a square. So that was the general idea going into our code here. Now the issue here is, okay, so let me see what we're doing here. First calculate the squares, then after that so we are manually calculating each case setup, I think. So whenever we see a new value, we then iterate through all of the squares. That's what, and to get all of the possible bases it can give. And in the end, our answer is just gonna be like the base that has the highest frequency that can be used. So looking at it, we did 3,000 square root values. There's up to about 3,200-ish square root values to 10 million. And since we could like insert out up to 500, we could have tested up to 500,000 values. That's how we got the 1.5. Actually, was it 1.5? Yeah, 1.5 billion-ish, which is a problem. So what we could have done instead, and this is a little bit, admittedly this is a little dubious, we could try the 10 million list idea. So what we're going to do here is, let's see, kind of making this up on the fly, but we're not going to need this compute statement anymore since we're going to be pre-computing every single case. So let's do a ref table. Let's make a list and then append it there. Okay, now we have to try what... Now what we're going to do is we're going to iterate through every single base, and then we're going to iterate through every single index. and then we're gonna just keep increasing the possible base value until like the base times the given square we're trying out is too high. So let's see, we have to iterate for each square. So for SQU in SQ, or list of squares, base is 1, while base times SQU less than or equal to 10 million. And now our base can't be a square either, so if get none, so if it's not in, if it's not a square, then reference base times SQU and base. What this means is that we can use that value as a base. So for instance, if this was on 7, then we could use 1 squared as a base and we have 7. So if our base is 7, we're using values like 7 times 2 squared, 28, 7 times 3 squared, 63, 7 times 4 squared, you get the idea there. Once we've done that, that should be actually enough information. And we just do instead of using our previous thing, we just use our reference. Okay, first this has to actually complete in time. I think that might have been enough time, hopefully. Okay, well that's concerning. Okay, what's happened here is I forgot to actually increase base. We have to increase base, we're in an infinite. Okay, wait a second here. So done array init, print did I put an extra 0 here? Okay, done array initialization. And it finished base set as well. 230. Okay. This at least feels faster because now we have because everything after that is pretty much instantaneous. It will take half a second hops. The problem is that the first bit, at least on my machine, takes like a decent amount of time. But the thing is that the judge tends to be faster here. So it's worth giving a shot at least. Oh. I see, okay. Well, I need to move to the practice section, I think. Okay, then let's find the practice. Actually, wait a second. I could just submit in practice there. Okay. Can just run it on here first. Also, if it fails here, then we know that it's probably going to fail later on. Okay, time limit exceeded on that entirely. Yeah, that might be a problem. Okay, then that's definitely a problem. I mean, we do know that. Okay, that's like, we know in theory this should work. Like, we need to just get this like a factor of about maybe 5 faster. Okay, well, in our solve function, we've already removed the square values by default. So we don't need to be concerned about, like, if we divide by 1, we can know for sure that won't be a square, so it won't be the base. Thus, by this logic, that always removes some of the cases. So we can remove the 1 case. Now, if we can remove the 1 case, that means if we just consider the divisible by 4 cases, so there's divisible by 4, 9, 16, 25, and so on. There. It's safe to assume that at the very least we cut the number of overall lists in half. The downside here is that we have to probably store this in a dictionary. Dictionaries tend to be slower, but they very well could be at least somewhat useful. Okay. SQU equals SQ 4i's. Range 1 to when SQ. So in that way we don't include 1 in our case. Well, base times SQU is that. XB equals base times recurrent SQU. Now, if ref.get xb is none, then we haven't recorded this base yet. Ref xb dot add add in not the, is it the base? Yeah, it's the base. Oh, and there's one more thing. If ssq.get base equals none, because we need base to not be a square value. And we can start this at 2 as well, which isn't going to help much, but it's just for sake of being efficient, I guess. So if ref.get I is not none, then you point into this. And lastly, we also need to include I since I could be a base as well. The I is 0 and then the I plus 1. Okay, now we try this again. This should go a little faster. 3, 4, 5, 6, 7, 8. Okay, 8 seconds. That's definitely more promising. It's at least worth a shot here, I'd say. So just run it on the initial one. If it passes there, then it's definitely promising. Okay, it's successfully executed. I don't know if they changed the time limit for this problem or if it's on Python time limit. Since last time I remember the time limit was 2 seconds. If it TLE's the first one, then they didn't change it. Yeah, they didn't change it from the 1.98 from the 2 second. So that means we're incredibly close. We have to be insanely close here now. Now it's a question of just what is left. Like, improving this by just putting in a manual list is not going to really help us much. I mean, maybe you can get away with... Maybe there's something to be done here, actually. For base in range 2 to... Now this is a little bit tricky what to do here. $10 million. What's the highest we can allow base to be? 10 million divided by SQU. Plus 1. So then we keep it inclusive. 4, so 10 million over 4 would be 2.5 million. Yeah, that would be allowed. So then that way we don't need to manually increment here. Don't need to make those comparisons. If SSQ.getBase is none, yeah, that's probably easier than doing some really stupid scuff transitional. XV equals base times SQU. We can do XV equals here for a first one, and then XV plus equals SQU next. If that's none, then we go to the next one and just add in the new base. That should finish the base set. Hopefully that is fast enough. Okay, we need a colon here. Let's... Okay, now count it off. 1, 2, 3, 4, 5, 6, 7. Okay, that very narrowly improved it. Just barely. So let's go back to D here, run again. Yeah, now it's taking 3 seconds. Is there any other... Like, I feel like there has to be a faster way of doing this, but this also feels insanely close already. So it's a question of, do I want to just optimize the hell out of this, or do I... Or am I just better off trying to find an even more optimal case? Yeah, it's going on 2.442. It's just so close, and yet it's just off by a little bit. Like, is it really going to help me if I just remove 4 as well? Then I have to consider a 4 case in the later part, and that can get really, really screwy. Okay, we can figure out how many arrays are being made here. Can you take the length of a dictionary? It should, if this gives something in like the million range, then it works. Okay, 3 million. That's how many arrays we're dealing with here. It's divisible by 4. Yeah, the only way it's still... Yeah, it can't be a square. Okay, we can see how much of an improvement occurs with a square. For d dot get don't think this should make... I don't think this is going to make enough of a difference, but it could. Okay, if anything, that didn't even do any... That barely did anything at all. Oh, wait a second. This is base and range. We need 2 here. Okay, that actually is a pretty significant drop. 230. So we can try this here. So we've manually taken out the 1 computation and the 4 computation since they're incredibly common. Okay, this is running under the 2 seconds. So if this... Now, the thing is, this is only working because we have a really small input. With a larger input, I think we should still be fine, since 500,000, then we're only doing like another 1 million calculations there. So we can just manually take out a few of the really common ones, because a lot of those aren't going to be used. We can try this first. If this doesn't work, then you know what we're going to try and do next, which is we're going to try and do 9, then we're going to add 9, we're going to add 16, but we don't need that anyways, since the 01 lookup's enough. And there's the correct answer. This is quite a problem, isn't it? Yeah, normally my solve cap is around 2300 for these problems, so a solve on a 2470 difficulty rating is very nice. Since in theory I would be able to get this in the contest, I just took some of the wrong approaches at the beginning, and it just required a little bit of very scuffed optimization. It does also raise the question of if in C++ you would have to do this thing, which admittedly probably not, but then again, like looking at this, like this just shows that it's still very possible in Python. Like, I guess the way I describe it is C++, you can solve the problem even with some suboptimality. Python, you can solve the problem. You just have to be you just have to be accurate. That's pretty much it. But anyways, that will do it for this additional segment of Squarified. And yeah, that's pretty much it. Unrated the additional problems from Starters 103 that weren't in Division 1 will be up soon enough. Okay. See you on Wednesday. Yeah, next Wednesday. Actually, there's also AdCoder, so maybe it's going to be Saturday.